Thank you all for coming and for the invitation. This is actually my second time taught in this building, and it's always nice to have a big screen and good audience. I was actually under the impression that I would be talking to the kind of same audience like 2 years ago, which were, I think they were data science or computer science undergrad students. And I prepared my slide that way. And by the way, this is actually my first time giving, I mean, I've talked about this topic before, but I have never taught to someone who's not a, say, chemistry major or chemistry PhD level. But then I was told that there might be some faculty, so hopefully this is the right level of the presentation, and please stop me anytime during my talk, and I'll be happy to answer questions. It's okay if I don't go through all the slides. At least I want you to feel that you can understand something. That's the goal of this talk. Okay, so this is the title of my talk that you got from your probably newsletter or email list. Obviously, this is a very, very generic and big topic, and I don't want to give you this impression that's the only way that machine learning can be used in chemistry or chemical reactions. Okay, therefore I updated my title a little bit. So this is a more well-defined topic. This is use machine learning-based method to accelerate simulations of chemical reactions. Okay, before I dive into that, I just want to say this probably covers, I would say, 30 to 40% of what machine learning can do in chemistry. The topics that I'm not gonna cover, I don't work on those, are, for example, chemical informatics. Those are, say, if you want to discover a new molecule, right? And you can look at the database that we're already using. And an example that I'll be giving you guys is, say, if we want to develop a new refrigerant. So what do? We look at all the refrigerant that we have already have. We look at all the refrigerant that we have studied but did not use, right? And then we put them in a database and we let computer do its magic. And then we come up with proposed new chemicals, and then we test it in the lab or in computers. So that's another, I would say, even slightly larger field than this. It has a slightly lower learning barriers, so a lot of experimentalists are using that. But here, for the next 45, 50 minutes, let's focus on this. My name is Rui Sun. I'm a professor in the chemistry department. Okay, so here, oops. Is there any way I can show the title, or that's a screen just blacked out? Or, oh, that's actually my screen. I got it. How do I? Okay. Huh? Yeah. Your setting is a little bit too fancy for a chemist. How do I? Oh. Well, let's leave there. I think the title is probably a little more important than whatever going to be there. Okay. All right. So here, I'm a chemist. I'm interested in chemical reactions. That is the definition of what a chemist should be interested in. So here I just took the definition from Wikipedia, right? A chemical reaction is a process where you would have atom rearrangement. The idea is that you have old chemical bond breaks from your reactant site, and they rearrange. They form new molecules. That's called your product. Usually accompanying this process, there is energy transfer. Usually that is released in the sense of work done or heat transfer, correct? And that's why they are so important to our society. Therefore, since we're talking about atom rearrangement, therefore, this is how chemistry or chemical textbook usually present to you, correct? You saw some molecules, you have some elements, and then you see the arrow pushing here and there, as if that is how the chemical reaction is happening, correct? So you guys have taken some chemistry class, so you should have seen one version of this or something like this. Okay. Why? Oh, okay. And like I said, we are interested in chemical reactions because they're very useful to us. The most ancient example that we can find from history is the use of fire, probably started by some lightning event, correct? And the documented history of us taking advantage of chemical reactions can be dated to almost 2 million years ago. That's a really, really long time. And ever since that time, why we care about chemical reaction has actually not changed much, right? Summing in all, we're interested in these three questions. How do chemical reactions occur? If we want to start a fire, let's hope we don't have to wait for the next lightning rod, right? And how to predict the behavior of chemical reactions. If I have a fire, I want to control it, right? I want to move it from one place to another. I want to have a bigger fire when I'm cooking, when I'm boiling water. I want to have a smaller fire while I'm just maintaining it until my next meal prep, correct? So this is the fundamental questions that our predecessors have, and that's exactly the question that the chemists and chemical engineering are dealing with in a modern factory or labs. How to control them, how to make them more efficient, more useful. Okay, therefore, it comes to how can we study chemical reactions, right? Chemists over the years have learned to probe into the chemical reaction by saying, you can see, okay, how much heat I'm generating? What is the volume change of my system? Is there any color change? If I change my condition, right? How does the outcome of a chemical reaction changes? You guys have probably gone through some chemistry labs. Those are the things that you were told, right? And you can measure the speed of a chemical reaction. So this is a really non-fancy version of what chemists do to a non-major, right? And if you are a chemist major or you have gone through some of our advanced labs, you can see nowadays the equipment has become way more advanced. We're not just caring about the color, the energy, the volume change. You can actually use sophisticated equipment to probe into some sort of, okay, what does the bond looks like, right? What does the vibration of the molecule looks like? What kind of signal can you get? There is a whole field called spectroscopy, just studying that. However, there's 2 points I want to make. Number one is, as sophisticated as these measurements are, they are good to measure if you say, I have a chemical here that is stable, that is sitting in this beaker, let's measure it, correct? But it's very difficult for you to measure the chemical reaction starting from species A to B. This process is very difficult to measure, and I'll come to that later. So in other words, even this very sophisticated method, right? You can measure your reaction, you can measure your product, no problem. But really what's happening in between, you cannot see, okay? And because of that, as I have just told you at the beginning, chemical reaction really is atom rearrangement, correct? That's just a one sentence summary of what a chemical reaction is. As sophisticated as these things are, they don't really look at atom rearrangement. They look at atom arrangement, right? That tells you what this atom is connected to in what chemical bond, but they don't study atom rearrangement. So therefore, I call this kind of an indirect measurement of chemical reaction. They're very, very useful, as we'll show you later, but they don't tell you the whole story. Okay. Then the question is, well, why don't we just actually study the actual atom rearrangement instead of studying its arrangement? The answer to that is actually, it's not that we don't want to, it's just far too difficult to today's technology. Why? Because number one, the subject that you're measuring is far too small. Okay, we all know atoms are really, really small, right? And we're not even talking about electrons who governs the chemical reaction, right? They're too small. Second is the reactions are way too fast. Usually they happens on the orders of 1 trillionth of a second. Then you may ask, all right, so you say this chemical reaction is so small, but why, say, my organic chemistry lab takes 5 hours, correct? So that's a very fair question. My answer to that is, in your organic chemistry labs, let's say you are measuring your reactant A and reactant B together. You are waiting for the product C to be crystallized. Okay, so let's just say that's your entire five-hour afternoon, what it's gonna go to, right? What's really happening here, and I'll talk a little bit about that later, is when you mix two things, right, and you would assume A and B will react, a lot of them are collisions. So A molecule would collide with B molecules. A lot of them are actually non-reactive collisions, right? Because the ratio that a collision would lead to chemical reaction is so low, that's why you have to wait for a very, very long time. And that's one reason why we want to study chemical reaction, so you don't have to wait that long. Okay? All right. So because of number one, number two, you are left with this conundrum known as Schrodinger's cat, right? You really have this uncertainty. Until you do measurement, you don't know what it is. And even if you do the measurement, you cannot measure it precisely, right? Because the measurement itself induces some sort of change. This is the fundamental quantum physics. Okay, that's why we cannot do that on the fly in the experiment. All right, so let's kind of take a moment to summarize what we have talked about, right? We are interested in chemical reaction, which is atom rearrangement, correct? We can't do that, so we look at indirectly. What we want to do here is we want to come up with a way so that you can look at the atom rearrangement on the fly precisely, just look at it, what is happening. Okay, so how can computers help? Let's just switch gear for a second. Let's leave the territory of chemistry for a second, step into high school physics. Okay, what if you want to know the trajectory of a projectile? A trajectory, if you're not familiar with that word, is just a collection of position of the object over time, right? If I throw something, it's going to go up at the beginning before it hits the ground. It's going to travel some distance from me. Okay, this entire thing is called a trajectory. Okay, how do we get the trajectory of this projectile? What do you need to know? You need to know two things. Number one is the initial state of the system. That is, what is the velocity you are throwing this projectile out, and what is the leaving angle? That's what you need to know, number one. Number two is just, I'm putting that in the most general sense, that is the rules that govern the motion of the system, correct? In this case, it's just a force analysis, correct? This is a very simple system. If we assume there's no friction between the projectile and the air, the only thing that's governing that is the gravitation, correct? So that is the only acceleration that you have. Everyone have passed high school physics, know you can actually solve for this trajectory. Once you have the trajectory, you have all the information that you need, right? You know how far, what's the highest point that it's gonna hit, what is the turning point, how far you're gonna travel, where it's gonna hit the ground. Anything and everything you care about, it's all there. Now what I want you to do is just imagine this projectile is an atom in a chemical system. What do we need to solve the trajectory of that atom is exactly the same thing how we solve the trajectory of this projectile. Two things. The initial state of the system and the rules that governs the system. The initial state of the system, actually these are two separate subfields in chemistry. The initial state of the system belongs to a field called statistical mechanics. And the rules that govern the motion of the system is called quantum mechanics. It also actually includes classical mechanics, but we're not going to go in there. There's a really good quote that I want everyone to know here, and I show this quote every single time I give a talk like this. So this quote was given by one of the most prominent, I would say, physical chemistry educators in UK. So he wrote a very famous STEMAC textbook. And this is his opening remarks. He said, Boltzmann, you guys probably have heard of this guy's name. We use Boltzmann constant, that's named after him. He said, Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Then you have Paul Ehrenfest, which is another very prominent P chemist. carried on the work, died similarly in 1933. Now it is our turn to study statistical mechanics. Okay, this is just kind of how challenging that field is, and really, a chemist have no communication skills whatsoever at all. Okay. All right, so let's say we figure out a way to do number one, to prepare the initial state of the system. And now the question is, how do we figure out the rules that governs the motions of the system? Okay, so these are called interactions between atoms. You know, there's going to be a few fancy words that I throw here and there, and I will actually have a slide talking about all different nomenclatures. But what you need to know, just looking at this very simple system, this is just 3 water molecules, correct? We know that, for example, if you have water molecules, oxygen and hydrogen have different capabilities of pulling electrons, correct? Then you would have a partial charge all over the places. And if you have partial charge, then you know you have Coulombic interactions, correct? So these are some fundamental physics, right? If we have a way to compute its interactions, we can compute its forces, correct? And quantum mechanics help us to achieve that. Okay, now let me first show you some products, then I'll go into how to generate that, and then how machine learning can help in that process. So we're interested in how atom moves in a chemical reaction as a result of these interactions, correct? These atoms don't just move at will. They move because there's a force exerting on that, and coupled with that initial velocity. So you just have this kind of, you have 2 molecules come and collide with each other. You go from two molecules become 1 molecule, correct? And then they're just vibrating, they're rotating, they're jiggling around. And eventually you will see some dissociation happens. I'll just let this animation play out. And remember, chemical reactions is rearrangement of atoms, correct? And if you recall what they look like at the beginning, they're well separated, correct? Come on. Yeah, you see, right? You see some dissociation happen. Now we have, starting from 3 atoms in one group, 2 atoms in another group, end up with 4 atoms in one group and 1 atom in the other group, right? This is the very definition of a chemical reaction. Now here, you are actually studying the rearrangement of atoms. You are actually studying chemistry directly. Okay, so let me show you how that was generated. Okay, so there are many atoms in a chemical system. If you think about it, every atom is moving under the influence of all the other atoms around it. Correct? Each atom will have some sort of interaction, either that Coulombic interaction or van der Waals interaction or chemical bond, whatever, right? They're under the influence. So let's just say this orange bead is the atom that we're interested in. And that is kind of immediate neighbors. Each bead is a representation of an atom. And then each atom will have an interaction with the atom that I'm interested in, correct? And that interaction can be solved with quantum mechanics. And outside, they are kind of far away. They have very small interactions. So I look at them as kind of a field. Okay, those ribbon thing is just the collection of all atoms that are not in the immediate neighbor list, which have the strongest interactions. Okay, so once the force, each individual force that exerted on this atom I'm interested in is solved, we can do some force analysis and calculate the net force that acting on this orange bead. Once you do that, and let's say that is just the acceleration A corresponding to the arrow pointing down. And from statistical mechanics, you can get its initial velocity. Okay, let's say you have both. What can you do is you can move forward in time by solving the equations of motion to get where the atom is after a small time interval and what is its new position and velocity is, right? This is just nothing fancy, just simple solving classical or Newtonian equations of motion, correct? So we can do that iteratively, just solving the positions. We go through the list of atoms in my system one by one, correct? Each is in an environment of its own that is governed by the atoms around it, correct? If we do this for all the atoms one by one, and we just push forward in time, little by little, we will collect a bunch of coordinates, right? That is, at the beginning looks like this, then evolve a little bit in the next frame. In each frame, we compute its force, we solve the Newtonian equations of motion, we move forward in time. We do this iteratively, right? And then you will have a trajectory. That is exactly how I showed you this previous animation. They were actually just a bunch of screenshots, right? Made of thousands, probably. And we just played them together. This is exactly how animations were made. Okay. All right, so before I go any further, and from here, the talk is gonna get a little bit more technical. Okay, so I want to set out some of the nomenclatures here. You will hear I talk about geometries, configurations, and coordinates. They're just same. I don't know. We have to create these three different terms to talk about it. They are just the position of atoms. Okay, where this atom is in my three-dimensional system. Forces, that is important because we need that to compute the accelerations. Okay, and you will hear me talking about the potential energy surface, or sometimes just potential. Okay, these are three terms, but corresponding to the same thing. This is just the energy of the system that is directly related to the force, which we need for accelerations. Okay, and I underline that because this is where the machine learning method is going to come in and help us to do a better job in solving for those. Okay, and then all three combined, collected, is called a frame. Okay, so for example, here I'm showing you two frames in a trajectory. And each frame, you will have coordinate. You will know what the forces are corresponding to this coordinate. And you know what the potential energy or the potential is corresponding to this coordinate. Okay, so that is called a frame. And the trajectory is just a collection of all the frames. Okay, now there are different flavors of what I just showed you. And if your research generates a lot of trajectories, that line of research is called dynamic simulations, right? We look at dynamically how the system evolves over time. Okay, there are different flavors of this, and depending on your target system, the level of accuracy that you care about, you can do bigger system, you can do smaller systems. Here, I'm showing you an example from our group working on big systems, and this is the formation of a vesicle in our body, okay? And as you can see, I don't know why the animation is a little jagged, but it looks pretty smooth on my computer. You can sort of see this guy moving, right? Let me play it one more time. It's supposed to be continuous, but you know, as you can see, you see particles diffuse and all that kind of different behaviors, and each color head shows you a different type of your lipid molecule. Okay, this type of simulation is called, we're interested in the dynamics of molecules. This kind of simulation is called molecular dynamics simulation, or MD. I'll be using that term quite a bit. Now, what we will be focusing on here is actually reactions. What I've showed you before, they can run very large system, but their forces are sort of limited to, okay, you can only do physical transition, which means you cannot break bond. Okay, if you want to actually break chemical bond, you need to go into the territory of quantum mechanics, and that is a much more difficult calculation to do, and that's why we can only work on smaller systems. Here, as you can see, this system have 10, 11 atoms, right? The previous one had 1 million. Okay, this one, you know, you can still do the simulation, but much smaller system, and you can see the atoms are rearranging. You can have chemical reactions right in front of your screen to look at. This type of calculation, this type of simulation, we need quantum mechanical calculations like what I told you before, But that type of calculation is also known as ab initio calculations. That is a Latin word, means from the beginning or first principle. Okay, so the way they name this is because they understand, as of say the early 1900s, they believe fundamental mechanics or Schrodinger equations is really you make the least amount of assumptions in solving those. That is from the ground truth. That's why this is called, from the beginning or ab initio. So this type of simulation is called ab initio molecular dynamic simulations, or AIMD. Okay. Now, I will tell you a success story of AIMD simulations. Here is one of the most fundamental reactions in organic chemistry. This is the SN2 reaction. Okay, how many of you have heard of this term before? Okay, you three doesn't count. Only you? All right, you guys are really not chemists. Okay, so let me take a moment to explain what this is. All right, this I'm not even gonna call that nucleophile. I'm just gonna call, here you have this red molecule here that carries a charge. And then you have this bigger group here that is another molecule. And the feature of this molecule is that here you have a carbon in the center that connected to 3 hydrogens. So that is a CH3 group. Now, if you think of this black molecule, what it does is this CH3 group sort of work as an umbrella sitting on this LG group here that it kind of protects it. Okay, so what happened is this red charge molecule collide with this big black molecule here, right? From the backside, will hit the top of umbrella. What happened is you will see a new chemical bond is formed from this red group to this CH3 group, right? And then kick out that LG group here. This is called actually a leaving group, right? And also in this process, the charge, which was carried from this red group here, was effectively transferred to this leaving group. This is one of the most fundamental organic chemistry that you can have, right, in the textbook. This is called a SN2 reaction, correct? That is a classical understanding, has been there for 100 years. No one challenged that, no one questioned that. This is how we know chemical reaction takes place if it were gonna go through this SN2 route, okay? And now here, you see, this is a more modern chemistry, right? What we do is, all right, if we assume this story that I told you is true, what does the energy of the system looks like along this process? The x-axis that you cannot really see is we call that reaction coordinate. What it does is from the beginning, which is on the left end, that is a reactant. From the right, on the right hand, that is a product. Really, what this tells you is just a picture representation of this story that I just told you. Okay, you start from the reactant, right? A green molecule comes in, hits from the backside, and it pops out this purple molecule there, right? And now the charge is on this purple molecule. And along this process, you can compute what is the energy of these different configurations. So that's really what this tells you. Okay. Now, if you believe this story, okay, and what we're interested in, among many other things, particularly is, well, what is the direction of the charge, correct? So if you can think of these 3 B's here, this is a cradle kind of problem, right? If these 3 B's here is this CH3 group, that is the umbrella protecting the leaving group, okay? And now if you have a bead comes in from one end and it's gonna pop out the leaving group to the other end, correct? So this common understanding leads to a question. If we define the direction of the velocity of this incoming group, this red group, as the forward, okay? So in this picture, everything traveled to the right is forward, okay? Now the question is, if this reaction mechanism were true, what do you think the velocity is of this leaving group? And, just looking at this, right? So this is just one critical comes in, hit with the 4, right? The 3 stays stable, and the 4th one would pop in the same direction because you have to conserve momentum of the system, correct? So the answer to that question is that, okay, I expect my leaving group, which carries the charge, to travel in the forward direction, which is the same direction of my incoming group, correct? This is the traditional understanding of SN2 reaction, and nobody challenged that until we actually can perform the experiment that is pure enough, it's clean enough, and precise enough, you can actually measure the direction of the leaving charge group. Okay, and I don't want to go into too details about this, but I want you to focus on the colored map here, right? The way to look at this map is just imagine the red group in the previous picture is coming in this direction, going from left to right. So this is the motion of my cursor, right? And then the CH3 group is sitting in the middle, okay? And this color tells you the direction of this leaving charge group, okay? Since most of them is on the right-hand side of this CH3 group, correct? So this is a pretty typical forward scattering, exactly like what we would expect from the traditional understanding of the chemical reaction. And you see that in our dynamic simulations, correct? Exactly like the way I showed you before. This is how it was generated. Let me play that one more time. Comes in, collide, and then this yellow bead slow because it's massive, it's iodine, right? But it is, you can sort of see it is, let me play that one more time. It is traveling in the forward direction, correct? The same direction as this pink atom comes in. Okay, so everything is good. You know, as the experiment develops, it checks out the theory as we have understand it. So this is a good theory. All right, now the problem is, okay, I run the same experiment. What I'm gonna do differently is I'm only gonna let these two beads barely move towards each other, right? Instead of colliding kind of with a high velocity, high collision energy, this time I can sort of quench my molecule so they move in slow. Okay, they're still colliding, but they're just kind of colliding. They're very slow. And you do the same measurement. What you have is, well, this is actually pretty non-selective in the sense of whether you have forward scattering or backward scattering, correct? You just see as much signal in the forward direction compared to in the backward direction, correct? And this is where the experiment, you know, that, like what I said, experiment can tell you what is at the beginning, what is at the end. And this is what is at the end, correct? How does that lead to the end? It falls short in providing an explanation. Now we can compute the same process using the same procedure that I showed you before, run this chemical reaction, and just see what happens, correct? And you perform this simulation, you see you got some sort of kind of weird reaction mechanism, right? Let me play that one more time. The same reaction happens, hit, but instead of just happens, this CH3 group to kind of hit it round about 360 degree and picked up the incoming ion from the other side, correct? And then because of that, where this charge group is traveling the backward, correct? Let me just play that one more time. I should have set it to be just continuous playing. Yeah, you can see this yellow bead again moves slow, but it is kind of dragging the feet, but traveling towards the backward, right? Just imagine you have enough trajectories behave like this, and also enough trajectories behave like the traditional way, and you combine them together. This is how you get a scattering angle looks like this. You don't really have an angle preference, okay? And this is really something that the world would have no knowledge of until we perform the dynamic simulations, okay? Experiment up until this day are not at this resolution that it actually can figure out what's happening at atomistic level. And by the way, if you want to, so these kind of simulations, and I'll talk about that, takes days, if not tens of days or hundreds of days, okay? But really, we're just simulating a few femtoseconds, right? How small is femtosecond? 1 nanosecond is 10 to the negative 9th of a second, correct? That's 1 trillionth of a second. And the 1 femtosecond is that divided by 1,000 and divided by another 1,000. So this is very, 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 very small, correct? Very, very, very short. Okay, so from this point, I'm gonna turn up another level of the technicality. Let me check on time. To tell you how this was generated. This type of simulation is called AIMD simulations. Like I said, you have statistical mechanics to generate this initial conditions of your trajectory, okay? And each step, you have to calculate the force. In this case, it's the ab initio potential. You use the force to update the positions and momentum. You do that iteratively until you're done. Okay, so it's actually a pretty simple procedure. You just do that a lot of times, okay? To generate a trajectory like that, like what I said, chemical reaction takes place on the orders of 10 to the 3rd femtosecond. Okay, that's a picosecond. And a single step, a step is defined going from one frame to the next frame. A single step can happen on the orders of 1/10 of 1 femtosecond. Why? That is because if you think about this, right? We compute the force acting on one atom according to its environment, correct? Now you know that environment is not rigid, correct? As the system moves just by a little bit, the environment all moved, correct? So the force you computed on this static environment is maybe an okay prediction of what's going to be happening within a very small time interval, but not for long, correct? Because the environment is going to be vastly different. That's why we have to keep the time step very, very small. And because of that, each trajectory will be involved tens of thousands of ab initio calculations. Okay? Well, that does not sound too bad. However, for this kind of simulations, because we cannot just collide them head on, right? Because we know in the experiment, they could be colliding head on, they could be colliding with some distance between the center of mass. They could barely just, touch each other and then just slice apart, correct? And that's one thing. The other thing is they could come in different orientations, right? If you have anything that's more than a single atom, you have a 3D structure, right? You can come in this way, back way, this, right? You have different orientations. And we're not even talking about the vibration phase, which is a little too technical. But the point is, to tell the outcome of a chemical reaction, you need to run a large amount of trajectories. Here we call that an ensemble of trajectories. Okay, that needs to represent some sort of a statistical ensemble. But the bottom line is, if you were to do this in the AIMD way, where all the forces are computed with ab initio method, we are talking about tens of millions of ab initio calculations per chemical system, and that takes 100 days. And that is, not doing it on your laptop. That is, you have access to a supercomputer cluster, and the computer cluster is relatively free. Okay, if every people is computing with the same resources, this can go on, right? And but unfortunately, this has been kind of the state of art in the last 20, 30 years. So how people were able to afford that? The way they can afford that is, okay, I know this is what I'm gonna pay, but I don't have that much. So what do? I'm gonna tune down, here we call the level of theory a little bit. I don't need my calculation to be that accurate because I cannot afford it. I'm just gonna forego a little bit of my accuracy so that I can run a little bit faster. Okay. Obviously, if that's the best you can do, that's the best you can do, but that's not ideal. Correct? And here that's the technical stuff I don't want to get into. Basically tells you that story. Okay. Then the question is, well, if we can replace these expensive ab initio calculation with some sort of analytical function or machine learning potential, that would be great, correct? And here this bead out of proportion, I think, tells you what kind of time differences are we making. Here, you see this FCMP2 DEF2 SVP. Okay, that's just one way of doing ab initio calculations. Each one takes 5 to 10 seconds. Okay, if we were to replace that with some sort of analytical function, excuse me, this screen is baking me. Yeah, if we were to replace that with some sort of an analytical function or machine learning potential, we're talking about not even a fraction of this time. We're talking about 2-3 orders of magnitude differences, correct? Here, I'll give you a real example that we did. This is with our collaborator, Professor Ralph Kaiser. He's interested in this astrochemistry reaction. This is believed to be one of the many reactions happens in the deep space, the star forming region. How did we, he say this is the way of looking at the origin of life. I think it's a little bit stretched, but the idea is that, when the universe was created, there was only hydrogen and helium, right? How did they come? Small molecules become, light element become heavy element, then you have radicals floating over the space. How do they collide first to make a lot longer chain molecules, correct? Life is only possible if the if the complexity of the molecule is up there is enough to carry all this information, right? So fundamentally, this is very important. How does the molecule grow in length, complexity, in deep space, right? Because that is actually at the beginning of what's going on in our biological world. Okay, now I don't want to bore you with the details, other than showing you that on the top left corner here, this is how the reaction happens in that traditional static picture that I showed you before with the SN2 reaction. And the bottom right here is our simulations. We can see they come in, they rearrange one another, and then you see some sort of dissociation happening at the beginning. Okay, I want you to pay attention to this small white bead. Eventually, you will see one going out in this direction. Yeah, you see that? Okay, so all right. So why do I pick this example? I picked this example because this is another example that experiment can tell you the initial and the beginning, and in this case, the initial and the final. In this case, the final is what is the probability of you capturing one of the product at a certain angle. What I have showed you before, there is this forward scattering, there is backward scattering, correct? If you were to break down the map that I showed you before, and you do a histogram of the probability of your molecule, of your particles at a specific angle, you will have something like that. Okay, that is figure A and B here. Now, the blue is what we get from AIMD simulation. The red is what we get from the experiment, what Professor Kaiser got from the experiment. As you can see, they're barely distinguished, right? That gave us confidence that our simulation is accurate, correct? They tell us the beginning, the end, we use that to verify, and then we can tell the story. We feel confident to tell the story of what's happening in the middle. Okay? So this is our AIMD simulation, right? We want to do it much faster. We want to develop a machine learning potential that can replace all the ab initio calculations. How do we do it is the question. And this is how you would do it. The title of this slide is Develop Machine Learning Potentials. What we have as a result of your AIMD simulation is that it generates a very large number of frames. And we told you what the frames are, right? Which together makes a trajectory. Now, if I can get a little bit detail here, I use the example of just a water molecule here, okay? This is what a typical frame looks like, okay? You have, atoms, you have oxygen, hydrogen, and hydrogen. And you have this, these three columns here tells you the coordinates. where this atom are, where these atoms are. And this tells you the gradient, like I told you before, that corresponds to a force. And actually the force is printed out here. So these are the informations that we have access after you run some amount of AIMD simulations, okay? And we're talking about millions, if not tens of millions of them. Our goal is to use them as input, to develop a very complicated machine learning based analytical functions. So next time we can run our simulations, instead of calling this ab initio calculations, I can just ask my machine learned potential what the forces are, right? And it can spill back the forces are so and so within a split of a second, right? Even much less than that. I'm not going to get into details how many flavors are there to develop machine learning potentials, but here the two examples that I showed you are both neural network based. The concept is that you provide some sort of a, let's work with the most fundamental one. You provide with some configurations. Here we'll have millions of them, right? They look into the features, they break them apart into different layers, and then they optimize this transmission probabilities. And eventually you get an output layer that just tells you, okay, here's the energy, here's the force, here's the gradient. Okay. Now, if we can do that, this is what typically developing a machine learning potential looks like. How can you tell a good one from a bad one, right? We provide these millions of frames into this machine learning protocol, and it does its job, takes a few days, and what it's reporting is it will look at some reference coordinates that hopefully not part of the training set and say, all right, this is the ground truth, which is the ab initio, say, energy force, right? And compare that with the same property provided with this machine learning potential, okay? And then you can, you also have a large set of this validation set, and then you can plot how does these two errors decrease over time. And this is how they decrease over time. And then at some point, you feel they are good enough, you just stop your training, you have a good set, you start running them. Okay. This is another way of looking at this, right? You run some trajectories from your ab initio calculation, you collect a set of your coordinate, and then you just plot the ab initio potential and the machine learning potential on top of each other, and you see they largely overlap. You see some different colors that showing at one position in a very small region, but not too bad. So with that, here I'll show you an example on how challenging is that. This is, before we step into the game, that's how people develop this kind of method, machine learning potential and run dynamic simulations. Here, I'm doing one simple chemical reaction that I just try to benchmark different machine learning potentials. Actually, Kazumi right there did 3 different machine learning potentials, and the error looks somewhat reasonable. Okay, you can't really tell one apart from the other. In our field, if you have an error like that, that's more than acceptable. You can just you just take that, run your simulation, nobody gonna question you. Okay, so the bottom line is all these 3 are fine. Okay, but if you run dynamic simulations, what you see is they actually generate vastly different dynamic results. Okay, what I want you to focus on is the 3 bars of each set tells you the reaction at 3 different conditions. 3 different conditions means they were colliding at different velocity, they are putting into different temperatures, things of that nature. And the height of the bar tells you the likelihood of the reaction to happen, right? Because like I said, not every collision leads to chemical reactions, correct? So if the AIMD were ground truth, then only the far left over there can somewhat resemble your result, correct? And these are the 2 methods which were pretty good with statistical errors, completely missed the mark. So from here, we see, although now we can get this simulation in a very, very short time, instead of waiting for 100 days, we just need to wait for 1 day. But, one may argue, what good does it do to you if it gives you a false result? And more importantly, if you don't know the ground truth, you don't even know its force, correct? You just all the error looks pretty good. You run it, you get some result, you analyze it. Do you believe it? Right? That is the question. So here, this is a kind of a catch-22 problem. If you have a large system, you can't afford AIMD, then you don't know the ground truth. If you don't know the ground truth, you can't really run your machine learning MD and say you get any result or not. That is what we're working on. We made some progress. But I do want to say, if you look at this curve, this dark green is the experiment. It ran this same reaction at different collision energies. Look at how many conditions are, correct? The AIMD, which is the ground truth, as you can see, we can only afford to do this tiny region if you can see it. There is a trace of red hidden behind these two curves. Okay, there is one red point here. But with the machine learning potential, we can actually expand it to much larger scale, and it agrees with experiment pretty well. I'm running out of time, so I'm going to skip some just to go to my summary. Okay. Dynamic simulations give us a way to monitor chemical reaction on the fly at atomistic scale. That is good. And machine learning potential could be used to develop potentials for dynamic simulations, but you need to be careful. It's only useful after careful calibration and benchmarking, right? They can accelerate this type of study without losing its accuracy. Unfortunately, there's too many people in the field just happy with any result, right? You run some calculation, you get some result, you report it, whether it's good or not, who knows? Okay, so we have other research programs in my group. They're well-founded. What I told you here is this dynamic simulations with machine learning. Really, this project is feeding into all other projects that we're working. If you're interested, you want to know more, come talk to me. With that, thank you for your attention, and this is my group. You see some of them here. So I'll take some questions if there are some.